We're good. All right, so we're going to be talking about Unit 2 today. I know half of Unit 2 was due last week. The other half is due this week. But we're just going to try to run through this to the best of our ability. If we have to pick up some of it next class, that's okay. Because I looked ahead, the next week's issue, or next week's PowerPoint doesn't look anywhere near that bad, so we should be okay. And two, we've hit. We've hit a lot of this information already, like in the introduction in Unit 1. Basically, we're just beating the horse freaking dead. You know what I mean? Like you have to bond the neutral and the ground in the main panel box. Anywhere other than the main panel box, they're going to be isolated to allow that ground to head cleanly back to the main panel box, to head cleanly to either the neutral on the weatherhead or to the ground rod to dissipate that high voltage. So we're just going to continue with that, Phil. Oh, actually, one more thing I should mention. When you guys are reading this book, right, it tells you every bit of code we're going through. Like this unit is going to go through 250 all the way up to like 250.32 or something like that. It tells you every code. It tells you every code, how they're written in the code book, and then the discussion part of it puts it into real human speak. So don't go trying to read this book in one shot. If you have to read it 20 minutes at a time to read a couple codes, read the discussions about those codes, and then sit there and think about it. Like, how is this applicable? I guarantee if you sit there and think about it for a little bit, you'll get it. If you read the whole thing in one shot, it might be difficult for you to think about a couple codes at a time. So perhaps try that as a studying aid. But this is a very good book. It tells you exactly what the codes are, and it puts it into human speak so you can understand them a little better. And that's all we're going to continue to do with this. So, Phil, I'm sorry for interrupting you.
Objectives. After studying this unit, the reader will be able to identify systems that are required to be grounded, those that are permitted but not required to be grounded, and those circuits that are not permitted to be grounded. Summarize grounding requirements for grounded systems. Explain how to size and install grounded service and system conductors.
Okay, and like I keep on saying, required, I mean, they obviously have to be, they're required, they have to be grounded. But things that are permitted, as soon as I see are permitted, I consider that to be, okay, this has to be grounded as well. Because I like to go a little above what the code asks for. The minimums are dangerous. Going above the minimum, you're always going to be in the clear.
Objectives. Identify system conductors that are required to be grounded. Explain the function and sizing of main and system bonding jumpers. Summarize grounding requirements for separately derived systems. Explain requirements for grounding two or more buildings supplied by a feeder or a branch circuit.
Now, just for an example, I guarantee you we can talk a couple, we've already spoken about most of these, so we can probably talk about it right here just to see what this says in the slide. So, conductors that are required to be grounded. Give me one conductor in your system that has to be grounded at some point. Give me a conductor that has to be grounded.
Neutral.
Neutral. And where is it usually where is it usually grounded or bonded? Give me two spots.
And if it's in the main panel box, it should be on a ground bar.
Yep. And that's a guarantee. You know what I mean? When it comes into your house, there's definitely gonna be a main panel box, right? You're not gonna come into your house in a sub panel, right? So it's gonna be bonded there. But where's another place that has to be bonded that we see all the time, but we're not actively thinking about? It shows it in every single slide, but I just want to make sure we're all on the same page when it comes to this. Where's another place that neutral wire is grounded?
Transformer.
Right at the transformer, right? If there's a transformer hanging on the pole, you will see a copper line chasing that pole down to the ground. And they bury that copper line with the pole. So that transformer is where the neutral comes off of that transformer. It's grounded right up there. And the second it comes into your house, it's grounded in that main panel box, all right? And that's the conductor that has to be grounded, right? The neutral conductor. Just think of the neutral conductor. Don't even call it neutral in your head from this point. Grounded conductor. Explain the function and sizing of the main system bonding jumpers. What's a big thing that we think about with those bonding jumpers? They don't have to carry the full load of the circuit, right? If we're bringing in 4-aught as our hots, our ground wire is not 4-aught, is it? No, why?
It only needs a holder plate in a split second.
Not a split second, but a second or two at most, perhaps, right? It doesn't have to carry that long term. It's not a continuous load. It doesn't even see power normally, under normal operation. Should there be any power going over a ground? Absolutely not. It should be a low impedance system. All right, so how do we size that, Phil?
Like I don't know, like number wise but like you said, doesn't it go off like the main, whoever's coming in?
If you look in the code book and if you look in the chapter, there will be a scale there that tells you for the size of power coming in, what your ground conductor has to be. Just like in commercial wiring, like Mr. Zarnoff, we use this as an example when you watch the video, you'll see it, but Mr. Zarnoff explains to you how you can measure a box, calculate the cubic inches within the box, and then figure out how many conductors can go in that box, right? And you can do all that by math. But this formula right here just tells you that. Because somebody already did the math. They wrote it down. There's a reason why we have pencils and pens and paper and all this shit. But if they can do it there, they can do it in this book. And they certainly have. It's very simple. If you look at your service coming in, it says I have 200 amps coming in. Okay, 200 amps has to be grounded with 4-gauge copper. How easy is that? No math or nothing involved. You just look at a scale. So you guys are electricians. You're smarter than hell. Are you going to know everything in that book? Absolutely not. But when the situation comes, are you going to know where to look? That's the important thing. Where to look. All right, summarize the grounding requirements for separately derived systems. What's an example of a separately derived system? Power coming into your house is not considered a separately derived. That's the service. That's from the street. What's a separately derived system? What's an example?
A generator.
Generator. Give me another example.
Battery box.
Battery box, right? Any different source of power other than the street, okay? And you usually have to ground those as if they're coming from the street. So the ground or the neutral coming off of that usually has to be grounded right there. And then continue into your house and then grounded again. Same thing with the battery box, okay? And explain the grounding requirements for buildings, for 2 or more buildings supplied by the same figure. All right, we haven't talked about that, we'll get to that.
Objectives. Summarize requirements for grounding portable and vehicle-mounted generators. Summarize requirements for high impedance grounded neutral systems.
All right, now these are the new objectives. We went through these past 3 slides, but 66% of this shit we already spoke about, haven't we? And that's going to continue. Sorry, I keep on bumping the percentages here. I've been doing that all day. Okay.
250.20 AC systems to be grounded. Alternating current systems are required to be grounded if the system meets any of the conditions in 250.20 A, B, C, or D. Other systems are permitted to be grounded. Compliance with Article 250 is required. Voltage supplied by the system is considered as a general rule. Using neutral for 3-phase systems is also considered.
Okay, let's see what the next slide has to offer.
Most circuits and systems that are not required to be grounded are permitted to be grounded. A few circuits are not permitted to be grounded. If systems are grounded, the methods must comply with Article 250.
Okay, so give me the example of a system that shouldn't be grounded. We talked about this last class. Just give me one example of a system that should not be grounded. How about something dealing with like a big, what?
Like machinery or something that has to run all the time.
Yes, something that you really want running all the time. And like we said about conduit presents what kind of a challenge? shit could hit the fan with conduit, can't it? Especially if something is vibrating, if that wire was improperly installed, because is there a chance that after years of that wire shaking in the conduit, that's casing, its insulation can be eroded away? Sure it can. And if there's a chance that it can be eroded away, there's a chance that it can hit the side of the conduit, right? Sure. Now, if that's an ungrounded system, there's no way for that to go back and provide an overload current situation for that breaker, so that breaker's never gonna wanna pop, all right? But now, the outside of that conduit is now hot. So if you were to touch that conduit and touch something else that's grounded, what are you? Dead, right? But why do these systems do that? What's the purpose? So, like Phil said, it can continue to run. So now we have a huge, huge three-phase motor running something. It's running a blower for like a furnace to melt steel. It's running a big motor keeping a conveyor going throughout an entire factory or possibly like an airport terminal. Something huge. Something that you don't want to fail. Even if it starts fucking up, you don't want it to fail completely. So what they'll commonly do is they'll put an alarm on each piece of conduit. So if that alarm senses, hey, we have power running through this conduit, that machine is going to continue to run because on one short, it's not going to fail. If two lines were to short, yes, you're going to have a short circuit. Yes, it's going to turn off. But if that one line fails, you can have a couple electricians come and work on that while that machine is still running, still producing, and that can be rectified without even turning off the breaker. So it's one of the few systems, that ungrounded is the way to go. Just like if you're in a crane, right? And you're working around like high voltage lines that can easily combust. I know that's not often. I know you guys aren't going to be working on a crane every day. But if you're working around things that can easily combust, you want that crane to be non-grounded. Because if that crane is grounded and that crane comes across that wire, that whole crane is now going to be hot and it's going to make that wire explode because it just got its way down to ground. It just shorted out that circuit. If the crane is ungrounded, it can just sit there and be hot. Now that's not good either, but at least you won't have an explosion. So there are a couple instances, but they are few and far between. For everything you guys are going to be doing, it's going to be grounded. And I can't stress enough, if it says are permitted to be grounded, don't even consider that to be are permitted. Just consider it to be got to be grounded. No other option.
Informational note, order grounded buffer systems. Systems are permitted but not required to be grounded. Must meet 150 volt test of 250.20A1. If grounded, must comply with the other rules of Article 250.
Yeah, this is an odd duck, and you're not going to see this too often, but phase C is just a neutral phase. Very rare, very odd. I doubt that you'll even see this in the real world, but just note that this is a possibility. Not likely at all, but is a possibility.
.250.28 AC systems of less than 50 volts. AC systems of less than 50 volts are required to be grounded under any of the following conditions.
I wish they would give you that in the slide. Yeah, where the primary voltage exceeds 150 volts. Because 50 volts is like the threshold, right? That's what they consider electricity to be dangerous above 50 volts. But as I just proved to you, if electricity is not dangerous past 50 volts, then who wants to go out and grab the battery in my truck? Anybody want to join me? No? Oh, that can hurt you too? Okay, so I just proved that to be wrong. So yeah, it does have to be grounded if the primary is 150 volts or higher. And that just means it's just stepping down, and that could be anything. That could be 120, it could be 240. As long as you have the right transformer, you can step down any high voltage to any lower voltage, okay? But just note that you have to ground it if that initial volt is 150 or more. But once again, I will ground it regardless. Part of the grounded, where the primary transformer is ungrounded, okay, that makes sense. And when installed as overhead conductors outside the building, that makes sense as well. Okay. why this is a terrible slide. Yeah, I'm not sure what they're trying to get at, volt to ground. I know there's a 250 volt limit that if you have 250 volts or more from a single leg to ground, then all your conduit has to be grounded with bonding bushings. I'm not sure what they're trying to get at here. But just so you know, this is the breakdown of a common system. Like I was just mentioning to Phil, on the street we have 7200 volts. In K, what's that called?
7.2 K.
7.2 kV kilowatts. Perfect. And that steps it down to 2 poles of 120. When you put them together, that's 240. This is common. This is what you see in every house. This is how they step it up. You only have one line coming down the street at 7.2 kV, and that's stepping it down to 2 legs of 120 or 240 from leg to leg. Once again, this is very common in industry. You have 13.8 kV coming in, and it steps it down to 2 legs of 480. That's not a very common system. Normally the total voltage between 2 legs is 480. Normally they're just 2 legs of 277. I really don't know what they're trying to get at there. Did you just read?
Yeah.
250.2B AC systems of 50 to 1000 volts. AC systems of 50 to 1000 volts that supplies premises wiring and premises wiring systems are required to be grounded under specific conditions where the system can be grounded so the maximum voltage to ground on the ungrounded conductors does not exceed 150 volts.
Yeah, these are all just systems that have to be grounded. This is an interesting formula right here though, and this is what throws a lot of people off. All right, how come in a house, I have 2 legs of 120, I put them together, I get 240? Makes sense, right? Adding, right? But if you're dealing with a Y or a delta, your 2 legs of 120 equal 208. What's up with that? Can anybody explain that? Phil, could you explain that at all? I'll admit, guys, it's hard for me to explain. I'm not great with transformers. At the core, all you have to know about transformers is they come in at high voltage, or they step it down, or they step it up. This is stepping it down greatly because I just told you that we're having, we have like 13K in the street. But you have to times the 120 by 1.732. And the way it was explained to me way back in the day when I asked this question, because I still have not gotten a great answer, but this is a Y system. It looks like a Y for a reason. They call it a Y for a reason. All right. This is your neutral, which is also grounded. Okay. You have 120 volts here, 120 volts there, and 120 volts there. Now, if I drew this perfectly, if you were to measure from here to here, just call it 120 inches. But if you were to swing that and move it over to the side, if you were to double that, 240 would be well out past here. So that's why the calculation, like the distance, if you were to move like that distance right there is 120. But if I was to slide here, don't do that. If I was to slide my hand out, where would that get you between there? It would get you more than halfway, right? So if you add a little bit more, if you times that 1 by 1.7, it actually gets you your 208. I hope to have a better way of explaining that to you in the future, but just know that when you're dealing with a 3-phase panel or a 3-phase transformer, that 120 plus 120 does not always give you 240. Just like a 480 system, right? You cut that in half, what's half of 480? You would think each leg is going to be 240, right? But each leg is actually 277. 2 legs of 277, when you put your meter on it, it gives you 480. But once again, if you're to times that 277 by 1.732, it will give you 480. So that's just how we get those numbers. As the weeks go on, I will have a better way of explaining that to you. I am still rusty with transformers. But all these systems are systems that have to be grounded. They're all typical systems. Nicole?
Systems 50 to 1,000 volts required to be grounded, where the system is three-phase, four-wire, delta connected, in which the midpoint of one phase winding is used as a circuit conductor. High leg identification required per 408.3 F1.
So this is a weird situation. This is when one transformer is bringing in two different sets of voltages. Because they put a grounded neutral in the center of this 120, right, in the center of this 208, this will actually give you true 240. But it's giving you two lines of 120 as well. So you can have two separate panel boxes. You can have one panel box coming in and it's just two 120s. You can have another panel box with three legs of 240. That's common if you want to run the receptacles and the light circuits off of 120, whereas you have like three-phase motors or bigger things that are operating things at higher voltages to keep the amps low. So there are situations that you'll have two separate voltages coming into the building off of the same transformer. And as we get further, this is very uncommon, but another very common one is called a wild leg. You'll have two 120s and one of 277. So you'll have one panel box, three poles, lines 1 and 2 are 120 volts and line 3 is 277. That's really common for a wild leg. This is kind of complicated. Let's talk about my wild leg. So why would you do that as a wild leg circuit? What would be the purpose of that? Why would I want two lines of 120, and if you put those two 120s together, you get 208. But that third leg, that 277, why would you want that 277 there and available? What does that give you? What are the benefits behind that? A wild leg circuit like that. Well, you still have 208 two-pole, right? So a lot of common things, like bigger things like a water heater, mixers in a kitchen, dryers, ranges. You can still run all that two-pole, 240 stuff, 240, 208 stuff, because you have two poles there. But at 277, why would you have that? What's up with that? The higher the volts, the lower the what? Amps, right? And you pay by the amp or you pay by the watt. So if you have a big commercial building, what's likely to be your biggest expense when it comes to power? Lights, right? So wouldn't it be nice if you can run your lights on 277 and you have two circuits available to run your outlets, which your outlets have to be 110. And you also have the option of making that two pole, so you can run things more efficiently if need be. So there are instances that wild legs are useful, but you really do have to label the panel box very well. You have to tell them what lines 1, 2, and 3 are. And the only wild leg that I've seen in person was actually at Simplex. I almost got killed by it because I wasn't expecting it. It wasn't labeled. The lights there are actually 277. Okay, who's up? Nicole, were you up?
I'm ready to go.
Okay.
250.21 AC systems of 50 to 1,000 volts, not required to be grounded. Electrical systems used exclusively to supply industrial furnaces for melting, refining, tempering, and the like. Separately derived systems used exclusively for rectifiers that supply only adjustable speed industrial drives.
And that's just what I was talking about. We're talking about big things like industrial melters, huge boilers, furnaces, which is the same thing as a boiler, or running huge motors with like motor control systems. Those are the ones that are not required to, because in reality, they can actually run full time. If one leg shits the bed, something grounds out, that system can still run, because it would be more detrimental if the system wasn't running. You know, like a lot of people could be without water now. Let's say that's a pumping station that's supplying all Scranton with water. Do you want that thing to shit the bed halfway through the day? Absolutely not. You might want that to be an ungrounded system. Or if you were working in a steel mill in Pittsburgh, you're just about to pour it, And the thing keeping all that steel nice and hot and melty just shit the bed. Now you have a whole bunch of steel that's just solidified in your bucket. You know what I mean? So there are instances that it's actually a safety risk for them to be grounded. Just so we understand that. But they are few and far between. They are not common.
Separately derived systems supplied by transformers that have a primary voltage rating of 1,000 volts or less, provided all the following conditions are met. The system is used exclusively for control circuits, qualified persons service the installation, and continuity of control power is required.
Yeah, so once again, you don't have to if you have all these available, but what's an easier solution? Ground. That way you're not worried about all these crazy codes. And normally an engineer will say, yo, this has to be non-grounded for this, and this reason. Okay, I'm with you on it, I agree. You're not gonna be making those calls yourself 9 times out of 10. That's gonna come down from a higher power. If you just wanna take this
Yeah.
as small.
Other systems that are not required to be grounded in accordance with the requirements of 250.20b.
So like we said before, for industrial electrical furnaces, for melting, refining, and tempering, rectifiers for adjustable speed drives, which just means VFDs, which is just variable speed motor control. We'll talk about that next semester. Separately derived systems for control circuits, which is once again motor control, and the systems under 250.20b.
Actual ungrounded system. Ungrounded systems are grounded through distributed capacitance when insulated conductors are installed in metal enclosures. Sputtering faults can cause transient overvoltages.
What's a capacitor? Anybody know what a capacitor is? I know we're digging back to fundamentals of electricity here, but what's a capacitor? What does it do? Hit me.
Doesn't hold an electric charge, it charges up.
Yes, but what's the thing about them? Do they hold like 100 volts?
No, it's low, isn't it? It's like a lower.
It could be
voltage.
crazy high. So like old tube TVs, it was very dangerous for you to disassemble them because inside there's a capacitor. You might have 120 volts coming in, but that capacitor might be able to charge to the tune of 30, 40,000 volts. And when you touch those two terminals, it discharges itself instantly. So that's what a capacitor does. It can store a tremendous amount of voltage and then also discharge that instantly. Just got the next slide.
Ground detection required for any ungrounded system from 120 volts to 1000 volts. Various types and levels of sophistication are available. NEC is silent on the type to be installed.
Yeah, and once again, this is like gray area. There's not gonna be a whole lot of systems that are ungrounded, but like I mentioned before, like you were supplying the water to all of Scranton, and we just had something ground out. It's still running, but something just ground out. How do you think we would figure that out? Do you think there's a guy there with a meter just checking conduits all day, every day? No, there's an alarm in place. An alarm could just be a continuity detector. Once it detects voltage on the line, it just screams. It could turn on a light. It could turn on a horn. It can send a signal to a guy in a computer bay 1,000 miles away, say, hey, we have trouble here. He calls up the electrician, hey, Unit 5 in Scranton, we have a ground, go and take care of it quick. But there has to be some sort of an alarm to tell you, hey, this conduit is now live with power. You must have an alarm for this type of ungrounded system, because you can see how deadly it would be if you didn't. If you touch that hot piece of ungrounded metal, and you went and touched the door on your way out, and that door is touching concrete, that's grounded. Boom, you're gonna get lit up. So they are very unsafe, but the danger is, you have to float it. You yourself being killed by that system, pretty bad. But all of Scranton losing power or water, also pretty bad. You know what I mean? So it's gonna be a risk and reward type of deal for those kind of systems. But once again, I can't stress enough, they are few and far between. You guys will not be hooking them up often, if ever. Who's up?
250.21c. Marking. Ungrounded system shall be legibly marked ungrounded system at the source or first disconnecting means on The marking shall be of sufficient durability to withstand the environment involved. 408.3 F2, ungrounded systems. Caution, ungrounded system operating blank folds between conductors.
All right, yeah, so I mean, that just makes sense, right? If there's a dangerous situation, you wanna alert anybody walking in that building, hey, this could be potentially deadly, all right? I know they haven't talked about it much, but, marking shall be sufficient durability. What do you think they mean by that? Marking shall be sufficient durability.
It won't be like weathered away and it will continue.
So writing in pencil's not cool, is what you're saying? Yeah. What about marker, Phil? What do you think about, I got those Milwaukee ink all, those things right, man, that's never coming off. Is that good? Oh, that can get scratched off though, right? So usually it's something that has to come out of a label maker. Normally if they're, the best thing you can do is like out of a label, like an industrial label maker, but with that like reflective coating, like you see on like the highway markers, like the green, like any light you'll reflect off of it. That's where you're gonna see a lot for these. So normally they have to be stamped on there. If you ever see something just drawn on in Sharpie, always be cautious because somebody obviously did not care enough. So they didn't care a lot elsewhere in that circuit as well. So your marking is just as important with these systems as your wiring method. You can't be too sure. Who's up?
250.22, circuits not to be grounded. Circuits for electric cranes operating over industrial fibers in class 3 locations as provided in 503.1115.
You don't have to say the numbers. It's well, I mean, like if you know what 503.155 is, I mean, you can throw out that reference if you want, but I guarantee none of us know what that reference is.
Circuits in the healthcare facilities are provided in 117 and 517. Circuits for equipment with electrolyte cell working zone as provided in Article 66.
All right, so things to not be grounded. I just made sense of that before with the crane, right? If that's a combustible fiber line and that crane touches that high voltage line and that line explodes, that can hurt a lot of people on the ground. So that's why the crane is ungrounded for that reason. But circuits in healthcare facilities, the fuck is up with that? This is healthcare. People could get hurt. Why in the world would you want an ungrounded system?
Because if it's something that has to run continuously, like life support, you don't want it shorting out.
Yes, yes. Your ground was intended to save people, but if something grounds out, that person whose lungs were getting moved by a machine, and that machine just shut off, and their lungs are currently not moving, what's going to happen to that person in 2 to 3 minutes? The answer's dead, in case you were wondering. Were you gonna add to that? I'm sorry.
No.
Okay, sorry about that. Phil?
Isn't it because of, like the arcing too? Like they're talking about like gases, like the Knowler's facilities that used to use gas. And like if it grounds out, it could arc.
Give it up. Give it up. I like it. I like that thought process. But yeah, all those are, everything mentioned here is reasons for not grounded. But do you see how slim that margin is? See how few of those situations are available? So ground until you're told to not ground. And whoever's telling you to not ground better have a good fucking reason behind it. But once again, that's us being electricians. We do a lot of things that might not even be in the code book. Like you put up a service on a house and there's windows everywhere. And you can't be within 3 feet of a window, but there's windows everywhere. You don't tell the inspector, oh, well, I just thought, if you go with a calculated reason as to why you did it, that's your variance. You know what I mean? So always have a reason why. Even if it's not to code and you did something a little weird, always have a firm reason why. And usually that reason, if it's founded in science, you usually be let go. Who's up? You up?
250.22 circuits not to be grounded. Secondary circuits of lighting systems as provided in 411.5A. Secondary circuits of lighting systems as provided in 680.23A2.
Oh yes, 680.2382, I know well. Yes, yeah, continue.
Class 2 load side circuits for suspended ceiling, low voltage power grid distribution systems as provided in 393.60B.
So let's put this into human speak, like what they're actually talking about here. The secondary circuits of lighting systems, whoever bought a light fixture in their life? Anybody ever buy a light fixture for their house? Okay. Anybody ever buy a light fixture that's LED? and it has a little driver in it. Anybody? So normally if it's stepping down to less than 30 volts, which normally LEDs are operating at way less than 30 volts, it doesn't have to be grounded, because that's a secondary system off of a system that's already been grounded, right? When you supplied this system with power, did you not bring a hot ground and a neutral to it? Sure you did, right? In that box you hooked it up to, you hooked the ground up to that box, didn't you? So there's not much more trouble that can happen upon that. You just can't and don't have to ground past that, because it's just getting stupid at a certain point. So just understand that on a lot of lighting systems, like for lamps, very small things, feeding just one small light, if it's less than 30 volts, they're not gonna require you to ground it. That's what that means, just so we know. And once again, that's a readout of circuits that don't have to be grounded. Once again, that's the light I was talking about, circuits for the crane, healthcare and life support, and the cells. Cool. This is secondary light circuits. Who's up?
System grounding connections. A premises wiring system supplied by a grounded AC service must have a grounding electrode conductor connected to the grounded service conductor at each service per 250.2481.
And now what I mentioned before, the utility transformer, there it is. There's that ground, that sneaky ground that nobody was talking about, nobody was thinking about. Now you can at least know. Are you ever gonna have to deal with that? No, that's the utility shit. We don't deal with that. We're only concerned with what touches our weatherhead and down. That's all we own. From the wires connecting to the weatherhead out to the street, that's all PPL's bullshit. It's all theirs. So they ground that transformer. When they're sending that neutral over to you, that neutral is already a grounded conductor. So you just have to make sure you ground it once again, because that's what we have to do, that's the law.
The GEC connection, required to be made at any accessible point from the load end of the overhead service conductors, service drop, underground service conductors, or lateral to, and including the terminal or bus to which the grounded service conductor is connected at the service disconnecting means.
This is a loaded question. Let me ask you a question. Is this meter base accessible for inspection? Think long and hard about that. Is the meter base accessible for inspection? What are your thoughts? He's shaking his head yes.
I think so, yeah.
Who agrees with this man? Raise your hands. Who disagrees? Raise your hands. Nicole disagrees, but with a questionable look on her face.
Yeah, cause I'm not sure
Is it-
what you mean by
Is it
base.
accessible?
It should be, right? Like, it's like right at the bottom of it and it's not completely thrown into like the floor.
Alright, so I have a little bit of insider knowledge on this. I know that that neutral connects right in the center. Right underneath that meter base. And if you're gonna ground that neutral, then there's a little lug off to the side of it that you can put a ground wire on in certain situations, and you can ground from that meter base too. But we were talking, I never talked about the meter base, did I? I always said that it's ground up at the pole off the transformer and in the main panel box. So why are they telling us that this might be an accessible spot for inspection? Is it? If I wanted to look at that neutral and I wanted to check out that ground, what would I have to do to that meter?
Pull the meter,
I have to pull the meter. And then what happens the second I pull the meter?
lose power.
Lose power. Is that, should I have to kill the power to be able to inspect something? No. So is it really accessible? No. Is it accessible to service it? Hell yeah. If I'm servicing it, I gotta do what I gotta do. And usually for me, working on a dead system is a hell of a lot safer than working on a live system, am I right? Am I wrong? But if it's accessible to inspection, it's something completely different. That's why houses now, like your ground wire that comes out, they want you to have a grounding bridge there. Anybody ever hear of a grounding bridge before? when that wire comes out of your main panel box, on its way to the ground rods, it stops just outside of your house, and it's a little terminal right there. It's called a grounding bridge. The ground just passes through that and goes to the ground rods as if nothing ever happened. But that grounding bridge is now an accessible point that guys from Comcast, guys from the water company, when they come to install their meters, they can ground their meters right on that terminal bar. Because what else would they have to do? They'd have to come into your house. And when they're doing all that shit, you're not even home 90% of the time. You're not even aware that they upgraded the meter or the receiver on your house. But everything they install has to be grounded. And versus them knocking on your door and setting up a time and waiting, it's an accessible grounding location. It's accessible to inspection or to service at any time without ever having to knock on the front door. So let that just be some food for thought here, please. I tell you what, this thing has been fighting me this entire class. Really well.
Generally accepted locations at the weatherhead for the overhead services, at the meter socket or current transformer enclosure, verified with the utility and electrical inspector.
Once again, that electrical inspector in this area, I guarantee you ain't gonna like the meter base. You ain't gonna like that, not one bit. There's only a couple instances where you have to, and they're few and far between. Continue.
At a wireway or auxiliary gutter on the line side of the service equipment within the service equipment enclosure.
So this is kind of odd, right? So like the line coming up here could be going to a weatherhead, or it could be coming off the meter. It could be both. Who knows? Because I don't see a meter here. The meter could be right here, or this could be directly to weatherhead. Who knows? Okay. But now coming in, we're coming into a bus bar, which is just like a terminal block that I was talking about in the last class. Both of these are given an even shot at that power, right? They both have an even chance of getting that power up there. Do they or do they not? There is no metering device. There is no overcurrent protection. If there's 200 amps coming in, there's 200 amps right there. Am I right? Am I wrong? Okay, I'm right. I'm always right. No, I'm not. These, now you're going to see that the ground is on that neutral, and the ground is on that neutral as well. Because if you think about it, these are both main breakers, or they're both main disconnects. They both have an even shot of power. Before, why the sub panel wasn't, because the sub panel was dependent on what for power? The main panel box. So the sub panel is just a large circuit, and you would never put the ground and the neutral together on an outlet, would you? Well, you wouldn't on a large circuit. But here, think of these as a main panel box. So there are instances that you can have a trunk feeding 1, 2, 4, 7 of these. The neutrals and the grounds have to be bonded in it because we're considering and we're thinking like each one is going to be a main breaker or a main disconnect as they are. So please understand that. Right off a meter, you see the meter, you see a big trunk in, and it's coming into a whole bunch of huge disconnects to feed whatever. It could feed a motor, it could feed another panel, whatever. But we're going to consider each one of these to be a main panel box or a main disconnect, which means that the bonds exist between the neutral and the ground. Any questions on this?
Outdoor transformer, if the transformer supplying the service is located outside, at least one additional grounding connection is required to be made from the grounded service conductor to the grounded electrode.
Is that shocking information to anybody? Have we said that 10 times already? Well, there's another slide telling you. Like I said before, that transformer, whether it's on a pole or on the ground, don't get lulled into just the pole, because this is a very old area where we live. Like where I was just at in Georgia last weekend, 2 weekends ago, whatever it was, I didn't see a pole in the sky. Because where my sister is, it's all new construction. Her first house there, it was just farmland. Some old buck owned, quite literally, hundreds of square miles of farm. And then when he passed away, gave it to his kids, and when they passed away, gave it to their kids. And all of a sudden, somebody started seeing dollar signs and sold off the entire farm. Everything there was new construction. We do new construction even here. Everything is underground. All your conduit is underground. Now, like I said, 7.2K volts underground. Why? That seems kind of crazy. We're not talking about grounding and bounding here. I'm just asking you a general ass electrical question. Why when we install new systems, especially new power lines, why are they always buried?
It's safer.
Why?
Well, the car smacks into power when it comes down, it's gonna kill someone.
And all the poles on the side of the road, I mean, if you're a drunk driver, aren't they like a magnet to your vehicle, right? You just like want to hit them, right? Not that I ever did any stupid shit like that, but that's what kills a lot of people, telephone poles, right? And more importantly, and more deadly than all, what's the biggest reason why they don't want overhead poles? Well, give me two more reasons. Give me a secondary and a huge reason. But the huge reason isn't so much for Pennsylvania. What are the guys in Cali worried about?
Fires.
Fires. And what happens when one of those lines gets blown down by a storm or when a tree falls on them? There's going to be arcing. There's going to be sparks. If you're in a dry environment, it's going to cause fires. Going to cause fires. What's another secondary thing that we're not so much thinking about? Something that you are going to be very considerate of in your new field.
Animals.
So as volts increase, right, it starts throwing off, I'm not sure, EMF?
Yeah, that's usually what everyone references.
EMF? Do you think your body likes to be around thousands of volts all the time, all day, every day? No. There's actually a zone that you can't build houses like that 500K line. There is a reason why they put it on the mountain. You can't have houses within a mile of it. Because if you live there and you're around that high voltage for your entire life, at a certain point you're gonna start growing a third arm. Now, I would love a third arm. I can't tell you how much crap I get done. You know what I mean? I wouldn't have to deal with Travis, hey, hold this. No, third arm, boom, right there. You know, but it's not good for you. The reason being, like a lot of linemen who are around high voltage, they can only do it for so long before they're forced to retire. So, another thing to consider as well.
Dual fed services, a single grounding electrode connection to the tie point of dual fed services is permitted.
Yeah, so this could be two commercial buildings. It could be like a split house, but I mean the way the setup is not for residential. This would be for a building, but you can have two weatherheads right next to each other and two services going into the same weatherheads, and if they're connected to the same building, you can use the same ground. It's not going to be the end of the world as long as you size the ground accordingly. That's going to be the only thing that matters. So just know that that is permitted, but it's not very often. Normally when you have two services coming to the same building, they are on opposite ends of the freaking world. You know what I mean? So there'd be no real need to combine that ground for that one purpose. There'd be a lot of wire wasted. So normally they would have two separate grounds, just as if it was two separate buildings. But just know this is permitted, but it doesn't happen very often.
Main bonding jumper is wire or bus bar. If the main bonding jumper is a wire or bus bar, the grounding electrode conductor is permitted to connect to the equipment grounding terminal bar. Facilitates operation of residual GFP system. Switchboards and switchgear may be supplied with this type of MBJ.
Load side grounding connections. A grounding connection is not permitted on the load side of the service. Disconnecting means unless permitted in Article 250. C 250.30 for separately derived systems, 250.32 for connections at separate buildings or structures, and 250.142 for other permitted uses.
Yes, 250.142, I know that well. Yes. Well, once again, let's talk about this again for the 30,000th time. The neutral up there, the transformer, whether it's on a pole, whether it's in your front yard, whether it's on your roof, whether it's in a cave, it's gonna be grounded off the transformer. It's also gonna be grounded in your main panel box, but that sub panel is isolated. The ground and the neutral are separate to prevent.
What? I'm sorry, I was typing.
All right, so
Sorry.
what kind of current don't we want going across that ground?
Injectional current.
Injection. Okay.
That's fine. Load side grounding connections, neutral terminal bar isolated from enclosure, equipment grounding conductor connects to enclosure.
All right, so yeah, like this, this main panel box wouldn't be, like, I would consider this to be a sub panel then. But that neutral bar, it shows up really close for the first time. The neutral bar has a bit of plastic underneath it, and it's actually off the enclosure. It's suspended, it's isolated off the enclosure by like an inch or two. And that's all it needs, because, you know, 208, 480, like if that were to arc, the arc gap would only be like an 1/8 inch. Like that low, even though it's high voltage, that low of voltage isn't gonna wanna arc very far. Like a 7,000 volt, that will arc probably, 13, it'll arc even farther. The higher the volts, the more potential it can for arcing. So that's isolated from the panel, and that ground, if you can tell, there's a lug bar there, and that ground is onto that. So the neutral is isolated from the enclosure, and that's a typical sub panel, and that just happens to be a 3-phase sub panel. Okay.
Hazard of using neutral to ground equipment. If equipment is grounded to the neutral past the service, a loose neutral connection will result in a shock hazard if a ground fault occurs.
Is there any shocking information there? Get it? Yeah, that was funny. I got a couple chuckles. Want to take this one too?
Yeah. Main bonding jumper. For a grounded system, a main bonding jumper must connect the equipment grounding conductors and the enclosure to the grounded service conductor within each service disconnect enclosure.
Any new information there? It's like the 31,000th time. But Phil, how thick does that grounding jumper have to be? That bonding jumper?
From like a 200, are you talking like a 200 amp, did you say from before, or just in general?
Let's just say in general. How would you explain that to somebody? So like, how thick should I make that? Why? Should it be as thick as it should be as thick as the hot conductors though, right?
No, but you should reference how thick the incoming conductors are, but you don't have to base it off the grounding or the bond or the jumper, because it only carries it for a couple seconds, so it's not, it doesn't have to be the same.
And where
size.
would you? So how would I figure out how big to make that then?
Referring to the NEC.
Oh, okay, cool. You see how easy that was? It's just looking up a chart. You have 600 amps coming in. Your ground has to be this size. Like I said, I don't expect you guys to know all this information off the top of your head, but I do expect you to know where to look. All right?
.24B exception. An unspliced main bonding jumper is only required in one section of any assembly listed for use of service equipment, usually furnished by a manufacturer.
Yeah, because this is a big switchboard, right? Or they call it gears, like a switch gear board. And each one of these mains, right, are isolated from one another, and they're in their own pocket. So like that main, you might just think it's a panel board and there's some wires behind it connected to some service bar. But in reality, that main is almost like a bulletproof, bomb-proof little cabinet compartment within the big cabinet compartment. So if there's something like an arc flash and an arc blast, we know that copper can expand at 64,000 times its original size. We know that can be 35,000 degrees Fahrenheit, which is higher than the surface of the sun. So we know there's a lot of bullshit that can be associated with that. So what they have to do is they have to make those to be able to handle that blast to the best of their abilities. So if shit hits the fan in here, Like, it's kinda like, I can't remember, it's runaway, thermal runaway? Yeah, thermal runaway, I believe that's what it's called. Like if like a Tesla were to crash, right? They're lithium ion batteries and and they come in cells. There might be thousands of cells. But if one cell gets damaged, just like with the Samsung phones recently, you remember that whole thing? It's called thermal runaway. Once one explodes or becomes damaged, that explodes and damages another cell, which damages another cell. Well, that same kind of thermal runaway can happen here. If this were to blow up and it wasn't encased with thick, heavy steel, all that heat in that explosion, is that gonna cause all these to start shitting the bed too? And pow, 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 pow. So think of how fucking dangerous, think of how dangerous one can be. Let's say this is 25,000 volts, which is not uncommon. Let's say there's just one blows up. That's gonna be deafening in the factory. Now, all these start lining up because one failed and it pushed that molten metal to everything else and started melting everything. So these are built thick and strong. Like look at the big green monster in the back of our shop. That thing's burly. And it's so thick and burly that if you ground one portion of it, it's pretty much grounded the entire thing just based on how strong and thick the steel is. And that's usually provided by the manufacturer. And anything made for electricity has to go through who? UL. So if it was manufactured and UL cleared it, then it's good to go for us. So there will be a lot of ground points that are put in by the manufacturer. Use them. Don't pretend like you're smarter than they are. Trust me, they're way smarter than we are. So, just so we know that.
Grounded conductor to service equipment. If an AC system operates at less than 1,000 volts and is grounded at any point, the grounded conductor is required to be run to each service disconnecting means and to be connected to it by a main bonding jumper.
Any questions there? Nothing shocking? Take this one too.
Grounded conductor brought to service equipment. Grounded conductor run to each service disconnecting means from wire line. Provides vital path for fault current to return to the source.
You can see here, it's all everything that I mentioned before. It's grounded to the box, grounded to the box. It's going through that. It's going through the ground. Taken care of.
Grounded conductor brought to service equipment. Grounded conductor to each service disconnecting means supplied from service drop or overhead service conductors.
So it's a common neutral there, it comes down, it's grounded and bonded in the mains. Like I said, these are two separate meters, so these both get an even shot at power. So we're considered both of these to be mains, but they're bonded and done accordingly. Now, if this is 100 amps and this was 100 amps, you would have to size this for 200 amps. Yeah, the maximum amount of power that can ever take. No. Who's up?
Grounded conductor brought to service equipment. Grounded service conductor required to be bonded to each service disconnecting beams for single phase and three-phase service disconnects.
I literally just spent 5 minutes talking about that before. Do we need to spend another 5 minutes talking about it again? Do you want to hear another rendition? No. Okay. Do you guys get tired of me talking? Do I get annoyed? Don't answer that. Colin?
250.24C exception. Grounded service conductor only required to be bonded to one section of listed service equipment consisting of more than one service disconnecting means.
Just like what I said before, this thing is made from the manufacturer. It was UL tested, it's been approved, so it's gonna work in any situation. And that metal is so thick and so burly, just one point of attachment is gonna be enough to get enough continuity wherever you have to go. Like this metal might be like 1/8 inch thick, like, and this thing could weigh thousands of pounds, just the shell, so it's burly. It can take that ground.
250.24C1 sizing for single raceway or cable. Grounded system conductor, often a neutral, is required to be not smaller than the conductor specified in table 250.102C1. not required to be larger than the largest ungrounded service entrance conductor. Rule contemplates all service conductors are in a single conduit, wireway, or cable.
Once again, I just beat that raw a couple times. Does anybody want a further explanation on this? No? Does anybody wanna go home? Yes, let me out of here. Who's that?
That's 250-24, sizing the single raceway or cable. Here's how. Obtain the size of the service entrance conductors. Use the size of these conductors in table 250 to determine the minimum size of the grounding system conductor. Compare to the size of the grounded conductor required from load calculation in 220. Follow instructions from design engineer. Install the largest of these conductors.
Now, apart from consult the engineer, which I will never openly admit to doing ever, because we're electricians, we don't like engineers. Screw them. But this is basically what I've been telling you. You're gonna take a look at your service coming in, which they're telling you the size of the conductors, but we already know how many amps are coming in, and the size of the conductors based on those amps. So we just take a look at the table and go from there. Now, if the rule is that if the wire does go beyond what that table can offer, you have to do 12.5% of the wire coming in. So if that wire was yay big around, I'm talking huge, let's just say theoretically, you would have to take, your ground wire would have to be 12.5% of this total area, which is a very small portion. But yeah, like the code tells you up to a certain point, like I think anything after like, 4,000 amp service, they might just say, okay, it's 12.5% of whatever is coming in. So just so we know that rule too. Just beating that raw. Oh, okay. This is a nice little exercise. Who's up?
Here's how. Ground service conductor. 350 kcmil aluminum service lateral conductors in each conduit. Table 250.102 C1 equals 2 AWG copper or 1 aught aluminum. Compare the size required by load calculation. Minimum 1 aught AWG for parallel installations. Install largest required conductor.
So now, once again, 2 gauge or 1/0. What does that 1/0 mean? I'm not sure if you said it. I wasn't paying attention to see if you said it, but what is 1/0? How do we say that?
Aught.
Aught, right? So gauge. I always grab this freaking marker every time. So gauge, right? It's gonna be 2, 4, 6, 8, 10, 12, and 14. You guys are really used to these two, 12 and 14. And we know that 12 gauge is bigger than 14 gauge, right? But as we get down this scale, it's like right here in the middle, it switches to odd. So like I said, as we get, when we're talking gauge, we're talking, oh shit, I can't say it. This is AWG. This is aught. This is MCM in my day, or now it's KC mill. It was MCM for a long time, and they switched to KC mill. But AWG or gauge, the smaller the number, the bigger the wire, right? Right here at the aught line, it switches between 2 and 1. So now this only lasts for 4. So it goes 1 aught, 2 aught, 3 aught, 4 aught. As those numbers get bigger, 1 aught can carry less current than 2. 2 aught can carry less current than 3, and so on and so forth. And then once we get past 4 aught, then we start getting into KC mill or MCM. Back in my day, it's just called KC mill now. But when they say 250, 300, 350, it gets really easy. How many amps do you think 250 KC mill can handle? 250. How many amps do you think 300 KC mill can handle?
300.
300. See how that gets really easy as that scale gets huge? But you just need to know this and this. For residential, it's very, very common. When I'm doing services, like a 200 amp service in aluminum, not copper. If I'm doing a 200 amp service, I'm running 2 4s and 1 2-aught. If I'm doing a 100 amp service in aluminum, I'm doing 2 2s and 1 4. So just please understand how that scale works. I know it's weird when we start jumping between these two very often, but please understand the difference.
Want to finish out? 3-aught AWG copper conductors, 200 ampere service disconnect. NEC requires 4 AWG copper or 2 AWG aluminum grounded conductor. Larger conductor may be required by load calculation.
In most areas though, they're gonna want you to run copper for your ground. Why do you think that is? Why do you think that is? What can handle the elements better? A naked copper wire or a naked aluminum wire?
Copper.
What can handle dirt better? A naked copper wire or a naked aluminum wire?
Copper.
Copper once again. Copper will oxidize, it's gonna turn green, but aluminum will literally fucking disintegrate if you leave it out into the elements. So that's why most places, like this said, the code, but I have never in all my days seen an aluminum grounding conductor heading out to a ground run. Never seen it, never, not once. What's the last one?
Yeah. 500 kC MIL copper conductors to 400 ampere service disconnect. NEC requires 1-aught AWG copper, 3-aught AWG aluminum grounded conductor. Larger conductor may be required if load calculation exceeds 300 amperes or 380 amperes.
But do we see with those 3 slides of how this works? How it's not the most complicated thing in the world? It just goes by the service power coming in.
More requirements. For service entrance conductors larger than 1,100 kc mil copper or 1750 kc mil aluminum, the grounded system conductor must be not smaller than 12.5% of the area of the largest service entrance phase conductor. This presumes all service conductors are in a single raceway, such as a wireway.
Well, once again, the book starts getting like complicated, like must not be smaller than. Couldn't you say must be larger than? Must not be smaller. Like it's like the book is just very confusingly written. But once again, like I said, at a certain point, the 12.5% rule comes into play. Let me try and get out here. Oh, it's 1.5%. Okay, we just covered that.
Sizing for single raceway or cable. For parallel sets of conductors installed in compliance with 310, if in one raceway, such as a wireway or in cables, determine the area of the largest set of conductors in parallel and consider as one conductor. Follow table 250 for the minimum size of neutral conductor. If the area of an ungrounded set of conductors is larger than table 250, apply the 12.5% rule.
Here's how.
Here's how. Add together the circular mill area of the largest set of service entrance conductors. Multiply this value by 0.125, 12.5%. The result is the minimum size of grounded neutral conductor.
Now here, let me just see what this next has to offer. Oh yeah, this is great. Perfect. I was really hoping they would show this. Good. All right, so at a certain point, right, we will start paralleling up wires to double up our power availability. What do I mean by that? So like you got the service rating of 1,000 amps. So they ran 3 400 kc mil lines for each leg. Let's say there's 3 legs. So there's 9 of these wires coming in, but they're all bunched up. So like if you run a 1,000 amp service and you ran like 1,000 kc mil, the wire would be so fucking huge and unmanageable. And like I said, you have to keep them all in the same piece of conduit now. Like, can you imagine how difficult that would be bending it, getting the conduit big enough for it? What's more common is to split that up into 2 or 3. So if we have 3 400 KC mills, what's 400 times 3? 1200, right? And that's, if you were to add them all together, that would still be well over the amount of size of copper that's there, that's in the 1000 KC mill. But it's gonna be way easier for you to bend 3 400s than 1000. It's gonna be a lot easier to put in the conduit. It's just gonna be easier in general. So when we start getting to big services, we'll actually start pairing up in 2s or 3s wire. Okay, just so we know that does happen. It happens fucking commonly. If you go down to AMT, you'll see that coming into the building. They had to double them up. So you just add up the total amount, and you do the 12.5% rule, and then it gives you your grounded size conductor. So, but just know that it is common, and it happens all the time. If you're looking for 1000 amps, you wouldn't necessarily bring in 1000 amp wire. You would bring in a couple wires that add up to that or above. Because you can see 1200 is a lot more than 1000. It has to be higher, or the same number or higher. Can't be close, can't be, oh, well, it's 50 amps under. No, it has to be the same or greater. Preferably greater, just to give yourself some leeway. The only faux pas is that these wires have to be the exact same length. They have to be the exact same length. Like even a foot can start fucking around. Because electricity takes all paths, but does not take them evenly. You know what I mean? If I have a 4-aught wire, a 12 gauge wire, and a 22 gauge wire, they're all vastly different sizes. And I can guarantee that if I touch the 12 gauge versus the 22 gauge, I get bit a lot harder on the 12 gauge than I would the 22 gauge. But power will be present across all of them. So when we do these, when we start butting them up, they have to be the same length, or that can cause trouble. Just so we know. I keep on forgetting where we leave off. Colin, you look like you are just itching to read.
Parallel conductors in 2 or more raceways or cables. Applies when conductors are installed in parallel in 2 or more raceways or cables. Grounded conductor in each raceway must be sized on the circular mill area of the underground conductor in the raceway. Minimum size of grounded conductor connected in parallel is 1 AWG. Table 250.102C1 to be used for sizing, other than for calculated load.
So these are coming in, they're buddying them up. But there has to be a neutral line that goes through with those 3 dots. We're gonna start to build magnetic fields, you can start building current, even these coming in. It shows that a neutral, like it's 3 wires of the same circuit, so you can't have, you know, like I've seen this, like guys like talk about like, well, I have 3 conduits coming in, and then buddying up these lines. Why don't I just have a couple lines of line 1 go to the first one, a couple lines of line 2 go to the second one? No, it's gonna start building weird current. The whole circuits, if you're doing a 3-phase, there's 3 hots and a neutral, and you're splitting them up, like you're doubling them up, then there's gonna be 2 sets of conduits going in, there's gonna be 4 wires coming in on one and 4 coming in on another one. You have to treat them as they're all the same circuit. You can't have more wires go on one than less. You have to have the neutrals pass through with it. Or you're going to start building electrical current, which means you're gonna start building heat, which means things are gonna start melting, and then things will start arcing. What time we got?
It is 11:48.
I don't want these videos to go past an hour and a half. Okay, we'll spend a little bit more time, but not much more. Who's up? You're up.
250.24C3 Delta Connected Services. The grounded conductor for a 3-phase, 3-wire Delta Connected service is required to have a capacity of not less than the ungrounded conductors. applies to corner grounded delta connected three-phase systems. The grounded conductor can be treated like a neutral or a 120, 240 volt single phase system and must be identified as provided in 200.6.
Like I said, this is a real oddball system that I don't even think that you guys will even see in the field. One light coming off that as a neutral. I'm just gonna go past that just so nobody gets confused. That's just so rare.
Grounding electrode conductor. A grounding electrode conductor is required to be used to connect the equipment grounding conductors, the service equipment enclosures, and where the system is grounded. The grounded system conductor to the grounding electrodes required by Part 3 of Article 250. Size the grounding electrode conductor per 250, both the section and the table. High impedance grounded neutral system connections are grounded in accordance to 250.
All this means is that one ground rod or one grounding electrode, like one does not fit all. You know what I mean? If you're grounding 1,000 amp service, it's gonna look a lot different than the puny little one we have in residential systems. Now the reason that one is 5/8, you know what I mean, it's gonna handle everything up to 200 amps. But beyond that, you might need a special ground rod or grounding electrode to fit the bill of what you're dealing with. You know what I mean? So all that means is there's just probably gonna change in length, but most importantly, in diameter. You know what I mean? Most ground rods are 8 to 10 feet long. And usually any bit of steel that's like slammed into the ground that's 10 feet in the ground or longer can be considered a ground rod as well. So if you have like a big, huge like pole barn, I say pole barn affectionately, but if it's like a steel pole barn, and it might be 40 feet tall. Well, if it's 40 feet tall, those beams might be in the ground 10, 12 feet. If they're in 10 feet or more, they can be used as a grounding electrode. And this just gives you all the codes for their installation and their sizing. But once again, we're not too concerned. You don't already know. There's still like 100 some slides, and there's no way I can talk about all of this, so I'm just trying to get the important information out of the way. Okay, this is good. This is good to know. Where do you leave off?
Material. Permitted to be of copper or other corrosion-resistant material. Permitted to consist of a wire, bus, screw, or similar.
Yeah, this is the bonding jumper from, this is the neutral bar, and that's bonding that neutral bar to the panel, right? There could be a couple of different methods. It could be a wire, it could be a copper clad. What do they mean by copper clad? What do they mean by that? You see the clad?
And copper on the outside, and it's aluminum on the inside.
Yeah, or any other metal on the inside. But the copper clad just makes it conduct electricity that much better when the outside shell of the metal is copper, because copper conducts electricity very well. They can also be a screw. You know what I mean? It could be it has to be green. It has to be able to be very visible from a mile away. But you can put that screw right through that neutral bar and drill it right into the panel box. But what's the caveat with screws? What do they have to be considered code? What's the issue with the threads, Nicole?
2 threads within the metal.
Yes. Yeah, so if the metal is 16th of an inch thick, you need 32nd screws, because you'll get 2 threads into the material. Perfect. Perfect, we're learning something. I like it. And that's the screw that I was just mentioning. looks just like that. I mean, not quite just like that, there's a couple different variations. Normally when you see that screw, it's not just in the middle of a panel box, it's usually on the top right or top left-hand corner of the service. And right where that neutral comes in, the screw is usually right below it in most modern panel boxes. All right, we're not gonna talk about this. Lastly, when we're hooking up ground systems, what are the preferred ways of hooking it up and what is the only non-preferred way from hooking up a ground? I mean connections, how do we terminate the ground? It has to be what? It has to be mechanical, right? It has to be a hard, firm, reliable connection. So if I'm gonna hook up a ground wire to a ground rod, how do I wanna hook that up? Do I just wanna like throw a couple zip ties on it and call it a day, walk away like a badass, throw my tools down, leave?
I think there's a clamp that goes on.
There is a clamp. For bonus points, what's the clamp called?
Well, I have no idea.
Acorn clamp.
Whoa! Hot shot over there. Alright, so what are other acceptable ways? You can go with an acorn clamp. Could you go with a bolt and a nut and a crimp fitting? Could you crimp a hook onto the end of a 4-gauge wire, hook that around a bolt and tighten that bolt down onto some metal structure that's going down 10 feet in the ground? Could you do that? Absolutely. Could you do an exothermic weld? Can you physically weld or braze that pipe or that wire to something for a firm connection? She's shaking her head. Who agrees with her? A welding process. Is grounding acceptable with a weld? It is. You're thinking solder.
Yes.
Yes, and that's what I was gonna get at. You just can't solder it. Because normal tin solder melts at about 300-400 degrees, and it melts pretty readily. Welding melts at the same temperature as the material itself. So if copper melts at 1200 degrees, that's what that weld is gonna start melting at. You know what I mean? Solder will melt at a much, much, much lower temperature than copper. So that's why it can't be utilized. So when you're doing your grounding, just make sure, I know solder is 9/10 of the law anywhere else. Like if you do a solder connection in a car, fucking reliable. You do a solder connection in a motor control board, fucking reliable. But as a ground, it's just a liability. Grounds, it's best to be mechanical or via weld, but the caveat with the weld is the material has to melt at the same temperature or higher than the wire itself. Solder will be much less. Any questions on what we discussed today? I know it was a lot. I know we can probably even continue to talk for a while, but I try to cap these at an hour and a half. Any questions? No? Okay, I'm stopping the video.